Okay, I think let's continue. Let's make one little extra tweak and see how it matters. Namely, if we look at our data here, the main idea was to, of course, one idea why it's this kind of roughly constant in the vertical coordinate is that we wanted to move from a two-dimensional problem to one-dimensional problem. That's one reason, but also we can use this for reduce the level of noise. Let's see what happens if we take the average of all the rows in this picture. Because roughly speaking, of course the paper has some structure and all that, so it's not completely constant, but roughly speaking, we should have the left part pretty much constant value and right part pretty much constant value. So each row is somehow a sampling of the same measurement but with a different noise. So in that sense, and noise, if it's zero-centered noise, if we take the average of the rows in this picture, the noise should pretty much cancel out and we should just have less noisy data. Let's see how well this works because the situation is not ideal. But maybe let's first extract the interesting part. So we decided when looking at the image, let's say we would have f equals, so we would take the middle row of the image, and then I think we decided that it seemed that this seems to be the column along the symmetry, or I mean along the middle where the step should be in the non-blurred signal. So here we could do something like from minus 128 up to plus 127. So now I think we should have a signal with length 256. So if this would be our f, we could plot f here, and we could actually call this f0, and f1 would be the mean value of the image along all rows. I think in MATLAB it works like if I apply the mean to a matrix, it will take the mean of every column and return a horizontal vector. I think. Let's see if that works. So here, let's put this with blue and the mean on top of it with red. Let's see what happens. So here you see I managed clearly to do the turning of the image so that the edge is vertical. I think I managed to do it quite well because it seems that we really can reduce noise a lot without kind of spreading the information more. I mean, if my turning of the image would be imperfect, then the edge would be slightly different in each row. And then when taking the mean value, it would spread out the data a lot more. But here, well, I was lucky or skillful, who knows. But anyway, here we see that the red line, in the red line we have averaged the noise away quite a lot because there are, let's see, what's the size of our image. So there are over 1,300 rows. So in each pixel in the red line we have averaged over more than 1,300 random noise components, and the noise has mean 0, so the noise is pretty much gone after this operation. And actually, I think probably we should call these, this should be actually not F, but M. So this should be M noisy, and this should be, let's say, M0 with a very low noise. So this would be M, let's have the low noise in blue and noisy like that. And actually we could also take a look at the more noisy image, but then I should have maybe done this cutting of the images to both images at the same time, because now it becomes let's try anyway. Let's take the more noisy one. This will not, maybe this will not be so easy, but so what's our most blurry and noisy? I think it's should be, I think this one. So let's do this one as well. So okay, what did we do? We opened this one, then we wanted to find this rotation as sharply as possible. Okay, looks pretty good. Open image, mode from color to grayscale, then first save as a Photoshop image so that we can retain the EAN code, and then let's cut to the edge part only like this, and save this one as a TIFF file, 16-bit TIFF file, and this should be called edge blur 3 noisy, for example. Okay, so that's there. And now, so this would be the low noise image, and then let's read the high noise image as well. So this would be, I guess, this one, but we should have a different name, say im2. And so maybe we should take a look at the image 2 as well. So this is now image 2. Can you see the noise? You see it's much more noisy because the ISO setting was 6400. Yes. Yes. I took halfway. End over 2, but I wasn't sure if it's an even or odd number of rows, so I added round. So halfway, roughly halfway. And now for this one, again, we should find out where is the middle line. It looks to be, it could be something like 1583. Let's go with 1583. 1583. So we have mn2, im2, we can again maybe take from the middle, and we take 1583 plus the same amount, and then if you do this with black, this with blue, and that with red, let's see how everything looks like. Okay, so now we have pretty much the same data, now with more noise. However, as you can see, the levels are not quite the same because, well, we don't know what all happens inside the camera. There must be some even non-linearities in the internal image processing of the camera and with the analog to digital conversion and all that happens there. So our levels are not completely reliable, so or not completely comparable. So we could do a little normalization step now here. Namely, we could here for each of these three functions take a first part up to where we are not yet in the blurred part, take an average of each of these functions separately along this line and subtract it, so that then it would be kind of near zero value, the starting point of the function. After that step, we could move on to the other end of our signal and then again take an average along many values here and then divide by that value. So then this end would be oscillating around the value 1. So then we would have kind of a bit more ideal situation, thinking of a step function going from 0 to 1 in the middle, but having these really measured signals that that represent our continuum model. So let's do that. Let's close the images for me. Close all and do here. And these we could call, let's put here an indication that these are the signals that have not yet been normalized. Like this, and here these are the non-normalized signals. And actually this is the high noise image. High noise image, and this one is the low noise image. Okay, and then let's normalize our data. So first left part to 0. I put it to quotes because it's so so vaguely said. But anyway, so let's take mn rho 0 equals the mean value of mn rho from 1. So this is to 256. So maybe let's go to 64 to keep clear from the center part where there is some blurring. We could do a bit more, but let's go with this one maybe. So maybe this one should do the trick. And like this, and also the final one, M0, M0. Okay, so let's see. So these are the zero normalized, or let's put left normalized signals. Is this what I called them? Yes, I think so. Okay, so let's see. So now you see on the left, we pretty much have what we wanted. So the signal is oscillating around the value 0. Then what we still have to do is the right-hand part, because there we still see that it's not really, the signals are not really comparable. But let's do them. Next. So then we should have just Mn, Mn2, and M0. So this should be Mn rho 0, 0, 0, and divided by the mean value, and not 1 to 64, but let's say 256 minus 64. I think this is not completely now a symmetric thing to do, but yes, that's more general, much better. And I think we should have 0 here and here and here. Does it look right? Ah. Yes. Okay, does it seem to make sense? Ooh. Let's see what happens here. So now we should just have this one, and this one, and these should be fully normalized. Okay, so now on the left you see we have 0 and they are near 0. On the right they are all kind of around the same value, which is near 1. So now from our camera data we picked out some data. Actually we have here 3 options. We have very low noise, kind of medium noise or smallish noise, and then really large noise. And all of them are really real data. Now this time, like I have been talking about M tilde coming from some device. Today M tilde really came out of a device. So these are now M tildes. We need to model in 2 ways, with the continuum model and with the computational model. And we kind of did the starting part of the work already in the beginning of the course, because our PSF, we designed our PSF so that it comes from this camera blur, 2-dimensional camera blur, but then restricted to a line of an image that's constant vertically. Exactly what we did today. So that's how we designed our PSF in the first place. And now I think our thing is to see how well our computational model matches the data we have. But just before doing that, this is slightly illogical still. We have this deconvolution third step, data measurement. But if we follow the usual way, we should actually have a different file where to plot the stuff. So let's save the results to file. save data. I think this should be deco 03, and I think we should save everything we are plotting. So im2 these guys and what else? We had the same guys with the 0 in the end, I think. And then I think we had just mn, mn2, and m0. So if we save those things to file, and actually then we should have something like data plot. Did I just save it or not? Maybe I did. Yes. And here we should actually just load the data and we should not have this stuff at all. Here just show the results of deco 3 data meas like this, and in the other one here we actually should not have any plottings. So now if we clear all and then let's run the data measurement part, then clear all just to make sure that everything works. Clear all and then data plot. Okay, so now we got all the stuff we have. Okay, so now we are all set for trying out our inversion methods for real data. So far we built up here the truncated singular value decomposition. So let's go with that. We will then turn to Tikhonov and total variation regularization once you have done your exercises this week, so that I don't give too much hints up here. So let's do what we did before. I think we should have, I think we did some, did we do it in one of the lectures? This one. Okay, so let's actually call this one now MATLAB. Let's put it to our deconvolution folder, and this would now be deconvolution 04 truncated SVD. So now we really do inversion of real data. And this should be comp. All right, let's keep the plot things here just for a while, and later do this comp and plot thingy. So now we should load the data. So now we actually don't simulate the measurement. We load like this, and we want only these. We only want these ones, our data vectors, and then construct computational model. We need a point spread function. And so the radius, I think we ended up by having 5 pixels. Yeah. Let's see what happens with this. And n is 256. And this we should call, let's call this f step. Just to kind of see if our measurement, because this time we know what the unknown is. I mean, we know because what we photographed. So let's just, for fun, let's compare our measurements to what our model is giving. Simulate the measurement. So we do this one. We don't need to simulate any noise. And we could now, for a minute, we could comment this stuff. And let's see, yeah, we have singular values, singular vectors. Well, let's suppress this for a minute. And here, what do we want to see? Let's make a new picture also here. This one, let's comment, and let's plot f step with black, and let's compare our data. Let's, for example, take this MN and see how they look like. Similar values. Okay. Let's still keep this commented. Oh, our step function is the other way around. Let's change that. It should be quick and dirty. Okay, so now our real-world data is carefully constructed so that it's close to something we can deal with analytically. And next, let's see how well our convolution model is behaving. Namely, so I think we have here, let's call this M simulated, and let's plot that. Let's move this up a little so it's we have this zero boundary. Okay, maybe we should. Oh, this is just.
These kind of boundaries with pictures, you like maybe wise to those boundaries like constant.
Yeah.
Like, or if it's really, changing, it's not constant, so it should be sometimes difficult to,
Mm-hmm.
But
Yeah, there we should. Yeah, there's now some trouble with the boundary condition. Um,
So instead it's 0 outside, it could be like the same as the last.
yes, yes, that would be one option really. But well,
That's enough.
if we don't care about that one, we can anyway see here. Uh, it seems to me that our radius is not perfect. We should maybe make our radius a little bit bigger in the point spread function. And why is it so linear in the middle? It's strange. How does our point spread function look actually? PSF, is it? It's just constant. Oh, but this is too, maybe this is an, we have this stupid, okay, we are not using the actual point spread function yet, okay. Yes, well, that explains a lot. Where is our, okay, here PSF plot. How should we do this? I'm completely confused. Anyway, this is something. This is not what we are supposed to be doing. Okay, let's see what happens with this. Okay. What is the PSF here? Oh, it's so long. Maybe this should be.
Want it to be 5, should it just?
Yeah, I think.
Even smaller a.
Should we go from minus a to a here, and if we have m equals 5, for example, should we then have here 2 times m plus 1? Something like this. Okay, and then we should normalize. Why is it not normalized? Clearly we need m more than 5. This is not wide enough. Let's put 8. Maybe even a bit more. Okay, here we have now we have a computational model here for our data. It's not perfect, clearly, but also our real data is not symmetric. I mean, the red line is not crossing the step in the middle as it should with this kind of symmetric model. Was this now the, which data point did we take? We are plotting mn, so let's try to plot m0 and see, maybe that will give a better idea. Not quite, maybe we should still use a wider wider.
Happens if we change A.
Oh, that's right. What does it really? Does it make a difference at all? I don't think it makes a difference really. I think it's the same shape always. Well, as we can see, our computational model is not really, and also our camera is not really giving such data we assumed. It's not symmetric. There's something weird in the data. Well, this is of course very usual with real data. There's something happening that our model is not really capturing. Maybe it's not too bad either. I mean, it's at least a little bit like that. Well,
I think the red signal should be translated just a little bit to the right.
yes, it would be.
Because
Yeah, that's true. That's actually, yeah.
you can actually compute the midpoint.
Yes, that would be a possibility too, for sure.
Maybe what we go with
I'll just go with trying a different one. Very scientific again. We could compute it, of course. Okay, and let's see this one. I think I did the wrong way around. Very scientific. It's just excellent.
Are you sure?
This is much better.
A value doesn't affect.
I'm not sure of anything right now, so let's.
I mean, if you now got this, what?
I'm pretty sure it doesn't really affect. I think the shape is the same in any case. But actually, I think this is already quite a good model. Maybe if we could even have here 10. I think this is not really too bad. I think this is already quite okay for a computational model of real data. I mean, of course, it's. Hey, but why our blue one should be in the middle of the step anyway? This is so weird. Why do we? Senhän pitäisi vaan pitää huolta, että nuo 1 ja 0 tulee oikein. Well, I think this is pretty good as a model. Of course, it could be a little bit better, and clearly the disk approximation is not so perfect. I mean, it seems that the actual PSF has a little bit different shape, and that's also something that could be calculated from the data. It could be really estimated from the that could be something that would actually make a nice exercise actually to dig it out of the data, a better empirical shape for the PSF. That's something. Yeah, let's do that. But anyway, at this point we do have now a method, so we can compute And let's MNY. Y.
The transpose of NP alpha.
Yeah, it should, but this is a square, so anyway, we can have it. It should be there, but oh, maybe this is the thing. Okay, that's much easier to fix. What's F? F should be probably F step. Ah. Where? Come on, stop it. Ah. Okay. Okay, so we do have now a reconstruction from small noise data and noisy data, and I think we can try to take more singular values. Let's see how the, do we have the picture? Yes, so I think we can use some more, like up to 30 or even 50. Let's see first 25. Okay, well, it is sharpening a little bit, I would say. Not too much, and also on the right-hand side end we have a big problem because our convolution matrix is assuming zero boundary conditions, which are clearly not true at all. So there we have some problems as well. But anyway, well, I'm glad to announce that this is our course's first reconstruction from real data, and we see at least some modest modest quality in the reconstruction. And we'll continue on Friday by looking at a bit more flexible and powerful methods than truncated singular value decomposition, maybe Tikhonov and total variation. Maybe we'll just go directly to total variation for the heck of it. Okay, so see you on Friday.